Okay, I think we're actually live online. Let's see if we can see some video coming out of here, and then I'll know. Oh, yep, we are. We have liftoff. So today we're going to be covering properties of Markov chains. I started to talk about this at the last section, but I'll get into some more detail. And one of the things we're going to do in this is a very important and particularly interesting topic is reversibility, which is really cool. Let me just kind of blow through a little bit of preliminary stuff. I think it said it last time, but I'm going to just do it again. So let's see. So let xn be a Markov chain taking values on omega, and let k be less than n two integers. Then the conditional probability distribution of xn given xr for r less than k is only dependent on k. So this might look just like the Markov property, but it's slightly different. What it's saying is this. So let's say you have a Markov chain. We're gonna be having a few Markov chains today. So I'll draw something that's long. Okay, so we have x0 and then x1 and x2 and then x3 and x4, x5, x6. Like this, right? Okay. It's saying, let's say you know x, you want to look at the conditional distribution of, say, x5 equals something, little x5, given, say, x and k for k less than 2. Now, if I said this for k less than or equal to 4, okay, then it would be just a Markov property. That's the definition of a Markov chain, that the conditional distribution of this given all the paths is only the previous one. But if I say the conditional distribution of x5 given, say, x2 and everything before it, well, it turns out it's still only dependent upon x2. It basically means that you can take these intermediate nodes and just collapse them. I mean, intuitively, what it means to have a Markov chain is that you can produce, say, x5 from x4 through some probabilistic rule, which gets you from here to here, right? So you have x4, you put it into the probability machine and pops out x5, right? Well, if I got x2, I can stick it in the probability machine and get x5. I just have to have a few more steps in my probability machine, right? But intuitively, this guy here can be produced by x2 plus some probability transition, okay? So if I subsample a Markov chain, it's got to be a Markov chain. The other way of thinking about it is that you can think of these as like people that are communicating. So this, I don't know if you've ever played this game when you're a kid, where everybody gets in line and somebody whispers something into the ear of the first person, and by the time they get it to the end, it's all corrupted. Like in the beginning you say, jelly beans are my favorite, and at the end they're like saying, Superman is really the best superhero or something. It goes from one crazy thing to some other crazy thing. It actually doesn't usually work, except for if somebody, okay. But it's like people whispering in each other's ear. And as it goes down, it changes. And they kind of wildly change, okay? But the point of the matter is that in each step, all the information passes through each node. So the only thing this person knows is what x3 whispered in x4's ear. All the other stuff that happened before here just doesn't matter anymore. So this is the state variable that encompasses It contains all the information about what's passed on to the next state variable in this probabilistic transition. Yeah? Well, those could be like hidden. That's why I'm saying that like you could have this sort of intermediate things that you could use as rules to get you from here to here, but you can always compact all those rules down to a single probability of transition. I mean, in the end, this is a finite number of states, and that's a finite number of states, and you can always represent the probability of going into this state for this as a number, okay? So all this stuff can be compacted down to a single transition matrix. Did you say reversible? Irreducible. Okay, yeah. Oh no. If it's an irreducible Markov chain, it means it can get into every state, right? No. An irreducible Markov chain. Okay, so if it's a reducible Markov chain, then it might stay in some subset of states, okay, forever, because it can't get out of them. It gets trapped. A reducible Markov chain is trapped, and an irreducible Markov chain is not trapped. Because the terminology comes from the idea that you can always take a reducible Markov chain and you can reduce it into like separate Markov chains associated with each of the trapped sets of states. The reducibility, okay, I think what you might, okay, your question is a good one, but I think you might be confusing the state diagrams. There's two kinds of state diagrams, and they're distinctly different. So this is showing transitions in time, okay? There's another state diagram I drew, which is in state, okay? So this is like 0, 1, let's say there's 3 states, this is 2, okay? And then I'll draw arrows like this. We're going to talk about these in a minute. This is going to be what's called a birth-death process. Okay? But this whole thing represents, this is just a different concept, because here it's like the variables are changing in time. It's like this would be a video. This could be a graphic animation. If I were fancy, I would do this as a graphic animation. You'd see the states transitioning, okay? So this would be, at every time, you'd move between these states. So this is different than this. It's like this state transition, this set of state transitions might apply to this Markov chain. There are different ways of visualizing different information. No, don't be sorry, because it's a really important point, and it's very confusing, honestly. Okay? This is showing each of the x0 here is a particular state at time 0, and this diagram shows how those states can transition. This kind of diagram only works for a homogeneous Markov chain, because the transition probabilities are a function of time. You can't really draw it this way. And typically you'll have a number here. So for instance, you'll say this will go up with probability 0.9, and then this wouldn't work because something has to happen. So there has to be another state transition here, which is back to the same thing with 0.1, because every time you start in state 0, you have to go somewhere, right? And then this one, this might be, 0.1, and that might be 0.9, because that's okay, because it's saying, okay, if I start in state 1, the sum of the probabilities of everywhere I have to go has to sum to 1. So this number and that number has to sum to 1. Okay, and then this guy here, well, okay, so 2, let's say this is 0.9, well then this would have to have another thing like this, which would be 0.1, okay? So that way, if you start in state 2, you have to go somewhere, okay? And if you start in state 1, you have to go somewhere, and you start in state 0, you have to go somewhere. But this is different than this. This is a different way of visualizing the information, okay? So, one way of thinking about it perhaps is, this is a little bit like more like a computer program way of thinking about it. And this is more like a signal processing way of thinking about it, really. Because, I don't know. Maybe that's not true, but whatever. It's a different way of looking at it. So, but my point here is that if you subsample this Markov chain, you'll get another Markov chain. Now, the other thing that's really, okay, so that's what this is. This is subsampling and conditioning, okay? Now, the thing that's really disturbing, and I mentioned it before, and in order to understand, I mean, you can spend a lifetime thinking about how disturbing this is, actually. Honestly, I feel like it's really one of the fundamental questions of our time in some sense. Is this issue of causality. Causality is something that I'm not really an expert on causality, but I feel that people don't have any understanding of causality. Causality is really disturbing because everybody feels like they understand causality, when in fact we have very little understanding of causality. Causality is, if you really think about it really deeply, is a very disturbing concept, because it really, if you spend enough time thinking about it, you'll suddenly realize it has an awful lot to do with the assumption of free will, which, without getting too philosophical, we all like to assume, because, I'd like to think I have some free will. I'd like to think you have some free will, but, I guess it's open to question. Maybe we're all just robots running, like biochemical Markov chain robots that are just, doing things. I'd like to think for those of us that aren't administrators, that's not the case. But the thing is that if you have probability kind of gives you this feeling of causality, but in fact, it's really an illusion, because you have the probability, so you have the joint probability of x and y, and that's the probability of y given x times the probability of x, right? But you could have just as well said that this is the probability of x given y times the probability of y. In fact, we have this sense that we feel that causality is related to time sequence. But there's no idea of time, per se, in random variables. They're just random variables. They're functions of a probability space, on a probability space, right? And you can condition one on the other or vice versa. It doesn't matter. So Bayes' rule is fundamentally a way of reversing causality. That, you just say, well, okay, that's P of y given x times P of x over P of y. So you can reverse that relationship, and you can just make x dependent upon y. It's a little disturbing, but true. So you can go back to this Markov chain, and you can basically do the same thing. What you can do is you can say, when I draw these arrows, what I'm really saying is I can write the probability of this sequence as the product of the probabilities of each of these transitions times the probability of the initial state. But I can just go and recursively apply Bayes' rule starting at the beginning and make this guy dependent upon that. Now, if I ask, well, what's the conditional distribution of x0 given x1 through x6, I can say, well, what's the conditional probability of x0 given xk for k greater than 1, right? And, it might be anything. But it's going to turn out that you can show that in fact, it's only going to be the probability of x0 given x1. It's only going to depend upon x1. if this was a Markov chain. And it's relatively straightforward to show that. I think I do it here. Let's see. Well, do I do it here? Yeah. Oh, here it is. Yes. 201. Okay. So reversible Markov chain. So we have do I show this? Hold on. I think these are these are out of order. That's why I'm getting confused. Okay. I'm not sure I prove it in the notes. Maybe it's a homework problem. But basically, you can start just going through it. Actually, it's going to be a consequence of something we'll show later, which is that we'll show that every Markov random field is a Markov chain. Okay? So, in 1D. Okay? So when we prove that, this reversibility property is a consequence, because we know that if this is a Markov chain, it's easy to show it's a Markov random field, because it's going to have a Gibbs distribution. This is like this is 2 chapters away, but I'm giving you a preview. And so if it's a Gibbs distribution and it's a Markov random field, that means that it must also be a Markov chain, but it didn't matter which way you looked at it, going this way or that. So therefore, it's got to be a Markov chain in both directions. So the bottom line is it's true. You can basically just go and you can reverse all the directions of dependency in the Markov chain, and you get this. I went off the screen. I guess I'll back up a little bit. You get this, okay? So you can just reverse it. So it's a Markov chain in both directions. Now, it may be a Markov chain in both directions, but it doesn't say what the transition probabilities are. So these transition probabilities, let's say that this thing is a homogeneous Markov chain, so it's Pij, right? Now, and let's say there's some initial state here, x0 is the initial probability, x0i I'll say, okay? So these are the initial probabilities. If I know the initial probabilities and I know the transition probabilities, and if it's a homogeneous Markov chain, then I know the probability distribution of the sequence of states, right? Because I just multiply the transitions all together and I get the distribution of the sequence. So then it begs the question, well, what's the distribution of the reversed Markov chain? Okay? Well, okay, if this is a homogeneous Markov chain, is this Markov chain going to necessarily be homogeneous? Well, the answer is not necessarily, because if this were in a stationary distribution, if this initial distribution is the stationary distribution of the Markov chain, then the distribution of each x will be the same, because it'll be in steady state. But if it's not in steady state, there's going to be a transient behavior, and then when you reverse the thing, it may not look like a homogeneous Markov chain. Remember, a homogeneity of a Markov chain does not imply stationarity. Stationarity means that the Markov chain's distribution is not a function of time. Homogeneity means that the transition probabilities are not a function of time. Now, it feels like if there's justice in the world, which there is no justice in the world, by the way, but it feels like if there's justice in the world, that if you run a homogeneous Markov chain long enough, it should become stationary. That's what we showed in the last class. We said if you wait long enough, and if you didn't do something unfortunate or dumb, it should have gone into a steady state. Now, what were the unfortunate or dumb things that could happen? Well, we could have had an infinite number of states, and all the peanut butter got spread to infinity. Okay, that's one thing that could go wrong. Another thing is that we could have had a periodic state, So then you would never reach a steady state because you'd be in this sort of periodic behavior, like a sine wave almost, right? But the other possibility is that you'd have reducible states. So you get trapped in some subset of states and you don't always hit the same stationary distribution because it depends on the initial state. But if none of those bad things happen, then if the homogeneous Markov chain runs long enough, eventually it will reach steady state. Okay? And if it reaches steady state, okay, then it's going to look stationary. So if we started off with the steady state distribution, it will be ergodic and stationary from the very beginning, and in those cases, then you would expect that the reverse Markov chain should also be homogeneous, okay? In any case, we can ask what the Q's are for the reverse Markov chain, okay? So we can go through a little calculation here. Okay, so what's the calculation? It's a very cute calculation. I love this calculation, although it can be confusing. Okay, let me do it here because I'll get myself confused. Okay, so this is a Markov chain forward in time. And so we're looking at page 202 and equation 927 and thereabouts, a little bit above 927. So we have the joint distribution of xn and xn minus 1 is going to be the conditional distribution of xn given xn minus 1 times the distribution of xn minus 1, right? So now, but I can write that either way. With Bayes' rule, I can write it as one condition. I can write it as a forward conditional distribution or a reversed, right? So now this term here, this is going to be Pij, and this thing is pi I. We're going to assume the thing's in steady state. And pi I is the steady state distribution. So, okay? And so in this case, this thing here is also going to be pi I, because we're going to assume that the distribution is in steady state. So if the distribution is in steady state, just to remind you, that means that pi times p is equal to pi. Right? Whoops. Where? Oh, there it is. Okay. Which is to say that if we sum over pi I times Pij over I, that'll equal to pi j, right? This is the full balanced equations. Full balanced equations. The full balanced equations are when we find a solution to the full balanced equations, and if the Markov chain is ergodic, right, then the solution to the full balanced equations will be the steady state distribution of the Markov chain. Now, so we're assuming this pi is the solution to the full balanced equations. So now we get equation 9.27. It says that the left-hand side of this is the forward Markov chain distribution of two pairs of states, and the right is going to be the reverse. So what we can do is we can define this reverse. We define that as Qji. It's the probability that we start in state J, okay, and we go to state I going backwards in time. That's going to be Qji. So if we use that notation, we get this result right here. I'll just write it out. It's that we get that pi I times Pij must equal pi j times Qji. This must always hold for any Markov chain. That always holds if it's a Markov chain that's homogeneous in its steady state distribution. In fact, it doesn't really matter what its distribution. That's true. If we have a Markov chain and and it's a steady state, then this will hold. Okay, this will always hold, where P is the forward homogeneous transition probability, and Q is the reversed homogeneous transition probability. That's always true. Now, the next thing is not always true. It may be the case, okay, that the forward Markov chain and the reverse Markov chain might have the same transition probabilities. It might be the case, yeah. Okay, let me go over this because this is a little bit subtle. So what are you asking now? Let's review it because it is really easy to get confused about this. Okay, so first of all, we're assuming that the PIJs and the pi's are the steady state solution to the PIJs. So they're the solution to the full balance equation, okay? So now we can write the joint distribution of two states in sequence as either Pij times pi I, because that's the forward, or we can make it this is really pi j. We can make it pi j times qji, which is the reverse, okay? Well, sort of. I think it comes more from the definition of the conditional probability, I would say. Oh, on which one? Now, the Pij does have an assumption of stationarity, okay? So, not stationarity, of homogeneity. Okay, and if it's homogeneous and if it's in its steady state distribution, okay? If it's homogeneous in its steady state distribution, that means that the probability distribution of pairs of states is not a function of time, right? So if that's the case, then the joint distribution is not a function of time, right? So if that's the case, then you could, well, one way of arguing it is that you could say, I mean, there's a lot of different ways you can construct this argument, but what you could do is you could say this. You could say, okay, well, it might be that you'd have that, hold on. It might be that you'd have that, over here you have that, it might be that Q here is a function of n. You're saying, how do I know it's not a function of n? It might be a function of n, right? There's some Q, because the reverse Markov chain, we don't have a proof here, but the reverse Markov chain is always a Markov chain. So there's always some Q. It could be that the Q is a function of n. So what I could do is I could say, oh, well, I do know that pi I times Pij is got to equal to pi j times Qn of ji, right? But now, nothing else in this equation is a function of n, so Q can't be a function of n. Now, I'm being a little fast and loose because some of these things could be 0. So if some things are 0, what can happen is this. If certain states are 0, then the value of Q could actually be indeterminate. It could be like, well, if you never enter a state, then it doesn't really matter what the probability distribution of exiting it is. Okay? So if you say, so in that case, there's some kind of fast and loose business that you have to deal with. Okay? But take my word for it. Let's assume that the probability of every state is greater than 0. So we get rid of states that are, well, in fact, if it's an irreducible Markov chain, then the probability of every state will be greater than 0. Because you have to always be able to have some probability of getting to every state. So therefore, no state can occur with probability 0. So if it's an irreducible Markov chain, all the pi's will always be greater than 0, and the q's, then q can be just written as qji of n is equal to pi I Pij over pi j, right? And that's sort of like what you're saying, Bayes' rule. And then clearly, this is not a function of n, okay? So, with a few more steps, I've cleaned up Yeah, you're right. I was being a little bit sloppy. So I cleaned up the argument, and now you can see Q is not a function of n. So if the Markov chain is homogeneous and it's in steady state, then the reverse Markov chain is also homogeneous and also in steady state. Okay? Everybody convinced of that? Okay, so now here's the key part, though. The key part is this. Now, so now, oh, that's what I was looking for. The key part is this. Okay, so now this equation always holds for any homogeneous Markov chain that's in steady state. That's always true. But now we can ask ourselves a question. We could say, well, look, if we go back in time, if we take the Markov chain and we reverse it, sometimes the Markov chain will have the property that it looks the same running backwards in time as it does forward. Now, do all random processes look the same running forward and backward in time? No. Okay? Here, let me give you an example. Just to give you an example, it's definitely not the case. So let's say we have the following three states. Okay? And this state, we transition back with probability 0.1, and here we go to 0.9. And then here is 0.1, and this is 0.9, right? And this is 0.1, and this is 0.9, right? So is this Markov chain, is this reversible? I know. Is this irreducible? This is a good exercise. This could be a homework problem. I should make it a homework problem. I may add it as a homework problem. Okay? Is this Markov chain irreducible? Why? What's the definition of irreducible? Yes, because there's always, you can calculate a probability. There's a probability. If I get from state 2 to state 1, okay, I can get there with probability greater than 0.9 squared, right? There's more than one way to get there, okay? But I know I can get there in 2 steps by going through these, I can get there. It's not impossible, right? So I can get from any state to any other state, right? So it's irreducible. Is it periodic? What's the definition of periodic? So let's ask the question, is it periodic with period 2? Well, okay, it's not going to be periodic with period 2. Let's say 3, because you might think it might be periodic with period 3, right? So let's say, is this periodic with period 3? So if it's periodic with period... Oh, I forgot to tell you last time. Yes, there's a very cool result, which I forgot to tell you about. I don't know how I forgot to tell you about it. That any 2 states that communicate have to have the same period. I forgot to say that last time, didn't I? Let's see. Okay. So, period state. Markov chains that communicate must have the same period. It's in my notes. Any 2 states that communicate have to have the same period. It's relatively straightforward to show that. Intuitively, it's like, well, because if they didn't have the same period, they would kind of interfere, right? So these all communicate. So they all have to have the same period. So I only have to check what the period of one of the states is. And if I find the period of one state, I know the period of all the other states, okay? So now, let's look at the period of the state 2. Well, maybe, it's too bad I didn't make that 0, but Let's take state 2. Oh, okay, we'll take state 0, the period of state 0, okay? Now, if, let's say it's not going to have period 2. So if it's going to have any period, it's going to have period 3, right? I mean, just intuitively, because the thing's going around like a clock, right? But let's say, so the question would be, is it possible, the definition of periodic, if it was going to have period 3, it means if you start in state 0 and you wait anything but 3 periods, the probability of being in state 0 has to be 0. So if in 2 periods, the probability of being in state 0 has to be 0. In 1 period, the probability of being in state 0 has to be 0. In 4 periods, the probability of being in state 0 has to be 0. For it to be a period of 3, it has to always be probability 0 of being in state 0 on any time other than a multiple of 3. Okay? Is that clear? I know it's a confusing definition. So the question is, in time 1, what's the probability of being in state 0? Is it 0? No, because you could have just stayed there. Right? In time 2, what's the probability of being in time 0? Well, it's definitely not 0. You could have stayed there 2 times. So this is not a periodic period. This does not have period 3. It doesn't have period 2. It doesn't have any periods because it can stay in state 0 forever. It's unlikely, but it can do it. For a long time, it could stay in state 0. So therefore, this is not a periodic state, and the states it communicates with are not periodic. So this is an irreducible, aperiodic Markov chain. Okay? Now, is it reversible? So if I actually wrote out the sequence, if I wrote out the sequence 0, 0, 1, 2, 0, 1, 1, 2, 0, would that be a valid, would that be a sequence that could have occurred in this Markov chain? Okay, you know, that's not so unreasonable, right? If I reverse this and write 0, 2, 1, 1, 0, 2, 1, 0, 0, can that Markov chain have occurred? No, because it required that you back up. This is like, you know, when I was a kid, when you had the wind-up clocks, you always, when you change the time, you always had to move the hands forward in time, or you'd mess up the mechanism in the clock. This is like running the clock backwards, because you're trying to go from state 2 to 1. You're like, okay? It doesn't want to do that. So this sequence does not occur with the same probability as that sequence. So this cannot be a reversible Markov chain, because when you reverse the sample paths, they look totally, they're totally different, right? Intuitively, the probability of the reverse path can't be the same as the forward one. So this is not reversible. Most Markov chains are not reversible. When you run them backwards, they look different. They're still Markov chains, but they have different transition probabilities. So, but one might ask the question, well, is it possible for a Markov chain to be reversible? Is it possible that the reverse Markov chain has the same transition probabilities? And the answer is yes, it's possible. What would happen? If in that case, you would have that P, you'd have that, if it's reversible, you'd have that Pij is equal to Qij. That the transition probability of the forward Markov chain is the same as the transition probability of the reverse Markov chain. If that's the case, then we could write this equation. We'd get that Pi times Pij equals pi j, and now here we have, okay, now you got to be kind of careful because this is ji and that's ij, so I got to reflip the j's and the i's here. So I'm going to get P of ji. So this is not always true. This is always true. And this is for reversible Markov chains, okay? If the Markov chain is reversible, this equation will hold. And this equation is very intuitive. It's so intuitive that many people think it's true all the time, but it's really not true all the time. It's only true some of the time. It says that the probability of going from state I to j, the rate, this is actually has the interpretation of being the rate at which you transition from I to j. So, this comes up, actually, there's a lot of, people get confused about this sort of thing. They go, you might say, oh, this actually came up, I was talking to somebody recently in some kind of conversation, in an ordinary, like regular human kind of situation, where people wanted to know, well, if you know the probability of some event occurring, if you know how often something occurs, do you know what the probability of it occurring given something else? And the answer is no, okay? Because there's two pieces of information you need to know. This represents the rate at which something happens, okay? Because it's the product of the probability that you're in state I and the probability that from state I you go to state j. And this is the probability you start in state j, and then from state j you go into state I. So this says that you okay. This is when let me go put this other diagram up. What did I do with it? Where's my other diagram? Okay. I had that nice little diagram. Now, what do I do with it? Okay, it's not here. Okay, I'll draw another diagram. Okay, hold on. Okay, so if you have two states, right? So this is, let's make it three states, 0, 1, 2, okay? And we're saying, okay, so you start at state 0 and you go to state 1, right? And this is P01, right? And then you start in state 1 and you go to state 0. So this is P10. And now we have something like this, say, and then we might have something like this. Oh, okay, I'll make that one go down to be consistent. And then you go up, and then you might also have this. Now, if you only know those two things, you know that the rate at which you go from state 1 to 0 equals the rate at which you say go from 0 to 1? Okay? No. Because you also have to know what the probability is that you're in state 0. Okay? In order to know the rate at which you're going from state 0 to 1, you have to know two things. You have to know the probability of going to state 1 from 0, but you also have to know the probability that you're in state 0. Right? So, like, the chances of winning the Indy 500 requires not just that you're in the Indy 500, but also that you're able to win given that you are in. So, like, okay, so this thing, so the rate, the flow rate is going to be pi 0 times P01, and the flow rate in this direction is pi 1 times P10. So if the flow rate is, so if pi 1 times P10 equals pi 0 times P01, that means the rate of flow from this state to that state is equal to the rate of flow from that state to this state. If that's true, you have like a balanced flow. Is that always true? No, it's not always true. Because, look at here. Okay, by the way, this has a name. These are called, so pi I times Pij equals pi j times Pji. This is called the detailed balance equation. The detailed balance equations do not always hold. They are not the same as the full balance equations, but sometimes they hold. And when they do hold, it means that the Markov chain is reversible. Is this Markov chain, do the detailed balance equations hold here? No, because the flow from state 1 to 2 is not equal to the flow from state 2 to 1. So if I put a cut through here, I will see a net flow. If I put a cut through these two states, the net flow I will see is 0. It's almost like some sort of osmotic steady state that occurs in like a membrane, as like something is flowing one way and the other way at the same rate, okay? So these are the detailed balance equations. Now the beauty of the detailed balance equations is this. If the detailed balance equations hold, then the full balance equations hold. So in other words, the full balance equations are a stronger condition than the detailed. Oh no, the detailed are stronger than the full. If these hold, it implies that. So to show that that's true, it's really easy. You just sum pi I times pij over I. Well, that's equal to the sum over I of pi j times pji. But that's equal to the pi j times the sum over I of pji, right? But that's just equal, this thing is 1. So that's just equal to pi j. And those are the full balance equations. So the detailed balance equations imply the full balance equations, but there are a stronger set of equations that hold when the Markov chain is reversible. So you'd say, well, why do I care? Well, it's going to turn out that there are a lot of interesting Markov chains that are reversible. In general, the name of the game is this. Someone gives you a Markov chain, and very often you want to find a solution to the full balance equation, because you want to know what's the steady state. It's like somebody gives you a differential equation, and they ask you what's the homogeneous solution to the differential equation. Someone gives you a Markov chain, they specify the Markov chain with the transition probabilities, and you'd like to know what the steady state is. One possibility, I guess, you go on a computer and just run it, but that's always a hassle, okay? So you'd like to analytically know. Well, in general, it's hard, because finding a solution to this equation is like finding a solution to, like, you're basically looking for the eigenvector associated with the eigenvalue 1, okay? This is the eigenvector equation for eigenvalue of 1. So it's hard in general to find, but sometimes it's easy. And one of the ways it's easy is when you can find the detailed balance equations. When you can find the detailed balance equations, then you can use those. If you can find a solution to the detailed balance equation, you can't always find it, but sometimes you can, and when you can, that gives you the answer to the full balance equation, so it's the solution to the problem. It's a steady state. Now, the classic example of that is what's called a birth-death process. And guess what a birth-death process is about? It's about birth and death. And in fact, there's an example here, birth-death process. So you can go through that. But we just have enough time. Do we have enough time? No, we're almost out of time. Are we almost out of time? Hold on. We have like one. So we have 1 minute left. Okay, so birth-death process. 0, 1, 2. Okay, I'll just do it here. So it's like this. And then the death, the birth is lambda, and the death is mu, okay? Birth is lambda, death is mu, okay? And guess what? It turns out you can write, this is a reversible Markov chain. You find the detailed balance equation, and you know that's the solution to the full balance equation. And the distribution looks like this. And guess what? It's stable when the rate of birth is less than the rate of death, or the rate of death is, hold on. The birth is less than the death, If you have more births than deaths, and you have exponential growth, then this thing's unstable. Unless you have a finite Q, and then it's stable. So this is very important. It's used a lot in queuing theory. And it's used a lot in, so it's very important. And it's very fun. So go through and do a calculation, and I always put one of those exam questions on, so it's always good to look at the birth-death process, because it's a nice thing to test. There's one more thing I need to go over, and I'll do it next time. Bye. And we're done. The one thing I wanted to go over